66 million years ago, a single rock from space came hurtling in and ended an entire geologic era. It's an almost unimaginable amount of power. So, today, we're going to dive deep into that universe-altering force. From the physics of total destruction and the clues that solved the greatest extinction mystery of all time, to the incredible science that now allows us, for the very first time in 4.5 billion years, to actually fight back. You know, it's the ultimate disaster movie plot, isn't it? But this is not fiction. The fall of the dinosaurs wasn't some kind of one-time fluke. It was the result of a cosmic process that is still happening all around us all the time. Understanding the day their 150 million-year dynasty came to a sudden, violent end is absolutely critical to making sure our own story doesn't meet a similar fate. And we got a very, very sharp reminder of that fact not too long ago. So that number, 1,500, that's how many people were injured, mostly by flying glass, when a relatively small asteroid, just 20 meters wide, exploded over a city called Chelyabinsk in Russia back in 2013. In cosmic terms, it was a pebble, but that pebble released 30 times the energy of the Hiroshima bomb and served as a chilling wake-up call that this threat is very, very real and very current. Okay, so let's get into it. Here's the game plan for our explainer. First up, we're going to get the terminology right, because it really matters. Then we'll break down the brutal, unforgiving physics of an impact. After that, we'll basically become detectives and look at the evidence that finally solved the dinosaurs' extinction. Then we get to the good part, humanity's first counterpunch, before finally looking at the amazing system we've built to watch the skies. All right, first things first. We see a flash in the sky, we call it a shooting star, right? But in the world of planetary defense, being precise is everything. What we call one of these objects depends entirely on where it is. Is it out there in space? Is it burning up in our atmosphere? Or has it actually landed on the ground? While it's just silently coasting through the vacuum of space, it's a meteoroid. Think of this as the object in its original state. It's the bullet before it's been fired. And it can be anything from a tiny speck of dust to a mountain-sized chunk of rock and metal. The very moment that meteoroid slams into our atmosphere at tens of thousands of miles an hour, it ignites into this spectacular streak of light. That light, the beautiful event we see and maybe make a wish on, that is the meteor. It's not actually the rock itself, but the fiery, brilliant result of it hitting our atmosphere. And if any piece of that object manages to survive that blazing, fiery journey and physically hits the ground, well, that's a meteorite. That is the cosmic messenger you can actually pick up, hold, and study. And if it's big enough, that's the thing that causes all the trouble. So what exactly happens when a meteorite strikes? It's not just a big hole in the ground. It's a terrifying, multi-stage release of pure energy. And it's all governed by some very simple and very, very unforgiving physics. You know, when it comes to impacts, speed is the real killer. The energy formula we all learned in high school, kinetic energy equals 1/2 mass times velocity squared, that's what makes this so incredibly devastating. That velocity squared part is the key. It means that doubling an object's speed doesn't just double its energy, it quadruples it. It's an exponential nightmare, and it's why even relatively small objects moving at cosmic speeds are just so incredibly dangerous. Now here's where it gets really counterintuitive. The danger doesn't all hit you at once. It arrives in this deadly sequence, in waves. First, traveling at the speed of light, is the blinding flash of thermal radiation, the heat. Second, ripping through the ground much faster than sound, is the seismic shock, the earthquake. And then third, arriving last and traveling at the slow speed of sound is that concussive blast of the shockwave. And that dangerous delay is exactly what happened in Chelyabinsk. Thousands of people saw a flash that was literally brighter than the sun, and of course their natural curiosity took over. They rushed to their windows to see what could have possibly caused it. And then, a full 2 minutes later, the shockwave arrived, blowing out those very windows and turning them into thousands of tiny projectiles. Okay, now I want you to apply that same physics, but scale it up 1 billion times over. That's what happened 66 million years ago. For a long, long time, the asteroid theory was just one of many ideas. That is, until scientists started finding these cosmic fingerprints at a global crime scene, cracking the greatest cold case in the history of our planet. So there were two main smoking guns, right? Two pieces of evidence that were just undeniable. All around the world, in the precise layer of rock that marks the boundary between the age of dinosaurs and the age of mammals, geologists found a thin, dark layer of clay. And it was rich in iridium, an element that is almost non-existent in Earth's crust, but very, very common in asteroids. And inside that exact same layer, they found tiny grains of something called shocked quartz. This is a mineral whose crystalline structure gets fractured in this really unique way that can only be created by the unbelievable instantaneous pressure of a hypervelocity impact. Case closed.
But recent discoveries have shown us something even more frightening. The sheer size of the asteroid wasn't the only factor. Supercomputer simulations trying to replicate the global extinction found that the angle of impact was absolutely critical. And as it turns out, it just so happened to strike at the single deadliest possible angle, 60 degrees.
This is what's so wild. This was just cosmic bad luck at its absolute worst. A steeper, 90-degree impact would have punched deeper but vaporized less of the surface rock. A shallower one would have had less penetrating power. But this 60-degree angle, it was the perfect sweet spot to both pulverize and eject the maximum possible amount of sulfur-rich rock from the Yucatan Peninsula high into the stratosphere. This created a global chemical haze that blocked out the sun and triggered a catastrophic impact winter that collapsed food chains across the globe. You know, the dinosaurs had no telescopes. They couldn't understand orbital mechanics. They were completely passive victims of celestial physics. For millions and millions of years, that was the story for every single species on this planet. But that story has finally changed. We have now become the first species capable of being an active defender of our own world.
And here is our first successful test case. NASA's DART mission was like something straight out of science fiction. We flew a spacecraft about the size of a vending machine across millions of miles of space to deliberately crash into an asteroid. The goal was pretty modest, just prove we could nudge it, shortening its orbit around its parent asteroid by a little over a minute. Well, the result was a jaw-dropping, astonishing success. We changed its orbit by 32 minutes. That's over 40 times more effective than the mission required.
So what happened? I mean, how did we outperform the estimates so dramatically? The mission taught us something absolutely profound. The nudge wasn't just from the kinetic impact of the DART probe itself. No, the truly powerful force came from the recoil. The tons and tons of rock and dust that were blasted from the asteroid's surface created this massive plume of debris that acted like a powerful temporary rocket engine, pushing the asteroid in the opposite direction. It was a complete game changer for planetary defense. Okay, so DART proved we can do it, but that ability is pretty much useless if you don't see the threat coming years or even decades in advance. And that, right there, is the job of the Planetary Monitoring Network. At the heart of this whole thing is a system called Sentry. So when you hear in the news that an asteroid has a 1 in 10,000 chance of hitting Earth, that number comes from Sentry. But it's so important to understand that it is not a panic button, it's not a doomsday clock. Its real purpose is to be a scientific tool for prioritizing. It flags newly discovered objects with really uncertain orbits so that astronomers all around the world know exactly where to point their telescopes next, with the specific goal of proving they are not a threat. And this exact process played out perfectly just recently. When an asteroid called 2024 YR4 was discovered, its initial fuzzy orbit put it on the Sentry risk list. But that's what the system is for. It triggered a global campaign of observations, and within just a few weeks, astronomers had tracked its path with enough precision to say with confidence that it will miss Earth by millions of miles. The system worked, quietly turning a potential uh-oh into a confirmed we're safe. But here's a really cool little twist to the story. While we are definitely safe from 2024 YR4, its new refined orbit shows there's still a small, but not zero, chance, about 1.7%, that it could actually hit the moon in 2032. It's just a beautiful little reminder of the incredibly complex gravitational dance that's always happening in our solar system. And that really brings us to the profound, fundamental difference between their story and ours. The dinosaurs lived and died by the whims of the cosmos. They were passengers on this planet. We are not. We have the ability to look up, to understand the rules of the universe, and for the very, very first time, to actually change our own fate. For the first time in the entire history of life on Earth, a species has achieved the awareness and the technology to prevent this specific type of planetary catastrophe. We have that power now. You could say we are the planet's immune system. The science is no longer in question. We know we can do it. So the only question left is one of will.
our collective will to keep watching, keep learning, and keep preparing to protect the only home we have. All right, welcome, challengers. So, you think you know everything there is to know about cosmic collisions? Well, we're about to put that to the test. This right here is a 10-question gauntlet, and it's designed to see if you've got what it takes to earn the title of Meteorite Impact Master. Let's see what you've got.
Okay, the rules couldn't be simpler. I'm going to ask you 10 questions. After each one, I'll reveal the answer and dive into the pretty fascinating science behind it. Your goal? A perfect 10 for 10. You ready? Then let the challenge begin. First up, let's start with the absolute fundamentals. We call a rock in space a meteoroid, and that streak of light in the sky is a meteor. But what's the correct scientific name for the thing that actually makes it all the way through and lands on Earth? The correct answer is a meteorite. And get this. While nearly 50 tons of space junk hit our atmosphere every single day, almost all of it just vaporizes. On average, scientists only recover about 5 actual meteorites a year, which makes every single one an incredibly rare find. So, did you get it right? 1 down, 9 to go. Now for the physics of a real-life disaster. Back in 2013, during the Chelyabinsk event, 3 different things hit the city, but at very different speeds. What arrived first? And more importantly, what arrived last? So the answer is the heat from the flash arrived first, and the blast wave arrived last. And this created a really dangerous situation. See, people saw this brilliant flash of light and naturally ran to their windows to see what was happening. But then, minutes later, the shockwave hit, shattering all that glass and injuring about 1,500 people. It's a pretty tragic lesson in impact. Okay, let's go from a modern event to the most famous impact of all time. For decades, the whole dinosaur killer asteroid thing was just a theory. But then, scientists found 2 specific pieces of evidence in a thin layer of clay all over the world that turned it into historical fact. What were they? Those 2 key pieces of evidence were iridium and shocked quartz. You can think of it like this. The iridium, which is super rare on Earth but common in asteroids, was the chemical smoking gun that pointed to something from space. But the shocked quartz, that's a mineral that can only get its unique fractures from an unbelievable amount of pressure, while that was the physical proof of a planet-shaking explosion. Together, those 2 close the case. So we know the impact happened, but why was it so devastating? Well, modern 3D simulations have actually pinpointed the worst-case scenario angle for that impact, the one that made it the perfect killer. What do you think that angle was? The deadliest angle was 60 degrees. If it had come straight down or at a really shallow angle, it would have been bad, but not as catastrophic. A 60-degree strike, though, was just brutally efficient at vaporizing a ton of sulfur-rich rocks and blasting them into the upper atmosphere. That's what triggered the global impact winter that really sealed the dinosaurs' fate. Halfway there, now for a really weird one. People will see a meteor and swear they hear a sound at the exact same time, which, should be impossible given the speed of sound. This used to be written off as just imagination, but it's a very real phenomenon. What's it called? This is called electrophonic sounds, and the physics behind it are just wild. The sound isn't actually traveling all those miles from the meteor. No, instead, intense, low-frequency radio waves from the fireball travel at light speed and cause objects right next to you, your glasses, your clothes, even your own hair, to vibrate and create sound. So you're not hearing the meteor, you're hearing your own surroundings being turned into tiny speakers. How cool is that? Okay, from a strange sound to the biggest, oldest physical scar on our entire planet. We are talking about the site of the single largest energy release event in Earth's history. What is its name? And the answer is the Rewrote Dome in South Africa. This thing formed over 2 billion years ago, and its original crater was a mind-boggling 300 kilometers wide. What we see today isn't really the crater anymore, but the deep crust that actually bounced back up after the impact. It's a massive geological scar that gives us a unique window right into the Earth's mantle. All right, let's jump from ancient history to humanity's first ever real attempt at planetary defense. NASA's DART mission was a huge success, but there was one key factor that made it way more powerful than anyone expected. What was it? The answer is the recoil from all the debris that got blasted off the asteroid. See, the spacecraft didn't just push the asteroid. The impact blew tons of rock off the surface, and that plume of debris, the ejecta, it acted like a rocket engine, giving the asteroid a second, much bigger push. The results? a success nearly 44 times greater than the minimum goal. That proved this technique is even better than we hoped for defending the planet. So when you hear that NASA has flagged a new asteroid as a risk, it sounds pretty alarming, right? But what's the real job of a system like Sentry? This question really gets to the core of how planetary defense actually works. The key thing to understand here is that Sentry isn't an alarm system. It's an uncertainty reduction system. When a new object gets flagged, the goal isn't really to warn the public of a threat. The goal is to tell astronomers, hey, we need to point our telescopes at this one. The system's true success is measured by the thousands of potential threats it allows us to confidently rule out, not by the ones it finds.
Just 2 questions left. This one connects geology right here on Earth to exploring other worlds. There's a crater in India that's basically a perfect natural laboratory for craters on the Moon and Mars. What specific type of rock is it made of that makes it so unique?
The answer is basalt. You see, most craters on Earth are in softer sedimentary rock, but Lunar Lake is the only one we know of that was formed in hard volcanic basalt. And since the massive plains on the Moon and Mars are also made of basalt, it gives scientists a perfect stand-in to study impact physics on other planets without ever having to leave our own. And here we go, the final question. This one is from the absolute cutting edge of asteroid tracking. An asteroid called 2024 YR4 is no longer a threat to Earth, but it turns out it might still hit something else very close by. What is that other body?
The final answer is the Moon. And this makes for a perfect final point, doesn't it? Planetary defense isn't just about protecting planet Earth. We have to watch the entire Earth-Moon system as one big, dynamic, gravitationally linked neighborhood. And that's it. That's the end of the challenge. So, how'd you do? If you got a perfect score, you can officially call yourself a Meteorite Impact Master. As this whole quiz shows, the story of impacts is really the story of our own evolution. We are no longer passive victims waiting for disaster like the dinosaurs were. We now have the knowledge to see these things coming and, most importantly, the technology to do something about it. So what is our greatest defense against these cosmic threats? Well, it's not some weapon. It's knowledge. It's the calm, persistent, methodical work of scientists all around the world who are mapping the skies to make sure our future is safe. And really, that's the ultimate takeaway.